Hello, everyone, we are the Federated Scope team from Alibaba Group. Today, we're going to introduce our work, FS-REAL, Array World Cross-Device Federated Learning Platform. It is proposed by Dawei Gao, Daoyuan Chen, Zitao Li, Yuxiang Xie, Shuchen Pan, Yaliang Li, Bolan Ding and Jingren Zhou. Our presentation is consisted of these sections. Now let's begin by the background of FS-REAL. Federated learning is a well-studied machine learning approach. It allows different clients to collaboratively train a model without uploading their private data. Generally, federated learning is divided into cross-silo and cross-device scenarios. In this paper, we mainly focus on the cross-device scenario, where the participants are a large number of edge devices. Typically, in cross-device FL, clients are mobile devices which is weak in communication and computation, but their numbers can reach millions. Meanwhile, the devices are diverse in their hardware and software configurations. Such diversity poses a considerable difficulty in effectively training models with FL. Fruitful investigations have been proposed for cross-device FL. However, we emphasize the following gaps between research and practical FL applications. First, most existing studies conduct FL experiments based on homogeneous device settings. Namely, each participated device has the same computational, storage, and communication capabilities. However, in real-world applications the device capabilities are highly heterogeneous. Besides, the available computational and communication resources of an FL device can change due to the competition from other apps on the same device and the spotty network connection. Furthermore, it's challenging to conduct research at scale with real heterogeneous devices. It requires researchers to deal with diverse device hardware and software environments to reflect real computing capacities. Also, they need build distributed communications through the network interface cards to reflect real transmission capabilities. Here we briefly compare some existing works in terms of heterogeneity, scalability and usability. We can observe that most existing frameworks cannot handle highly heterogeneous devices at scale with easy-to-use interfaces for both research and deployment. The missing of dedicated infrastructures obstacle further research and developments. Motivated by these observations, in this work, we aim to provide an efficient, scalable, consistent, flexible FL platform to bridge the gaps. Next, we introduce our proposed system, FS-REAL, in more details. Our framework is based on Federated Scope, an event-driven federated learning platform. To support large-scale heterogeneous devices, we make several improvements on Federated Scope, including server-side functional optimization and efficient runtimes on client sides, resulting in the new system named FS-REAL. Currently, with the help of MNN and OS-specific APIs, FS-REAL supports different operation systems and platforms. Specifically, FS-REAL supports Android, NVIDIA Jetson TX2 and Alios. Besides, FS-REAL supports different platforms like ARM64, ARMABI v7a and x86. We employ high-efficiency C++ underlying implementation, while providing easy-to-use Python APIs. In terms of communication, we have optimized the message transmission in FS-REAL by incorporating several gRPC compression algorithms such as gzip and deflate. Meanwhile, to efficiently and robustly support large-scale devices, we carefully optimize the server of FS. Based on the unified message objects, we analyze and handle potential space-time contention and redundant resource overheads, implement message transmitter and message processors in multi-processing. As the response times between devices can differ by order of magnitude in real-world cases, we propose a robust timeout mechanism for FL workload adaptation. Towards an easy-to-use and extensible FL system, We implement various advanced FL algorithms with unified interfaces, including async training, personalization and model quantization. In async training, to handle dropout clients, we add a dynamic time budget to control the training time. Specifically, the time budget is additive increase and multiplicative decrease. Besides, for personalization, FS Real supports RED to use methods such as fine-tuning and Fed Babu. Further, to reduce the size of transmitted models, FS also supports int8 and float16 quantization. FS Real is also able to monitor the training status in a user-friendly manner. With the help of WANDB, in server side, the training status will be automatically reported, such as training statistic, communication cost and device utilization. While in client side, we enable users to monitor training loss, CPU and memory usage with device-specific natives UIs. We notice preparing the corresponding hardware for heterogeneous runtimes to run real FL requires high costs. For example, in terms of development time, financial expense for acquiring new hardware devices, and potential loss of user experience. To accelerate real-world FL research and reduce the incurred costs, we provide a high-fidelity and easy-to-use heterogeneous runtime simulation platform in FS Real. Specifically, we focus on fidelity to computation, communication and storage capabilities of the participated devices. It allows users to run separate processes for the participated clients based on the Android official native simulation tool, and to configure the device capacities, such as number of CPU cores, memory footprint, network types and network latency. In addition, we provide easy-to-use configurable tools to quickly start simulated heterogeneous devices and run FL at scale. It supports to configure the global FL, client-level personalization algorithms and device capabilities. Here, we show some examples for advanced federated learning techniques, including asynchronous training, personalization, quantization and communication compression. Besides configurable tools, FS Real also supports to monitor federated training and configure hyperparameters in Android app. The Android app contains federated training log, device monitor and configuration, which allows users can specify their own data directories. While in simulation, we can disable the GUI and set up the Android app with Android Debug Bridge. Next, we will introduce 3 FS Real demonstrations. Now we first introduce our first demo, Android Runtime and Monitor GUI. Here we show a FS Real server and GUI server monitor, as well as the Android Runtime. First, we set up a FS Real server in the terminal. It will start a training task using the pre-configured YAML file with only one client. Now the web monitor receives the FL training task. Then we start a FS Real client and Android emulator. The Android device monitors both the training and system status. We can also modify the client configuration within the Android runtime, including training hyperparameters, data and communication configurations. Here we input the server IP address and set up a FL training task on FEMNIST dataset. As the logging panel shows, the client first unzips the specific dataset, then connects to the server. After joining the FL training task successfully, the client starts its training process. Here we speed up playing the process by 20 times. The server monitor will show the preset metrics in real time. In our demonstration, we monitor the test accuracy, validation accuracy, and training loss at the same time. Meanwhile, the Android runtime will also monitor its local training status. Finally, we can see that the accuracy improved accordingly. Then we introduce the Demo 2, Simulation Platform and Advance FL. Here, we will run a federated training task with 1,000 clients on the Twitter dataset. First, the simulation script will set up an fluorine monosulfide real server that listens on port 50,000. Then, on the remote machines, the script will check and install Android SDKs, Java SDKs, Python, and other necessary system packages. After that, it will start 1000 emulators on the remote machines and install the FS Real app in parallel. As with the previous demonstration, the FS Real Android app will be started and join the federated training task. The collected hardware information of the devices and training statistics will be presented in our GUI server monitor. Here the FS Real monitor shows the distribution of network speed, latency and number of CPU cores in our simulation. We speed up the federated training process by 50 times, and monitor the training statistics in the right panel. Finally, we finish the federated training with 1000 clients. Demo 3 is in real application on Car OS. Finally, we show the demonstration for speech recognition task on Car OS. The client app is tailored for the Car OS. For demonstration purpose, we show the training sample on the left and print the log of the app on the screen. The app will present the detailed FL logs on the right, and the training sample is shown on the left. After we start in fluorine monosulfide real server listening on port 50,050, and start the client app, the federated training proceed as shown by the log. Here we speed up the federated training by 8 times. Similar with Android runtime, the FS Real app will locally train the model and upload its weight update to the federated server. In conclusion, we introduce our released system FS Real. It is featured by the high usability and strong robustness for handling real-world cross-device FL tasks with a massive amount of heterogeneous client devices. We hope that FS Real can facilitate further real-world FL studies and applications, and our observations can contribute to a deeper understanding of device heterogeneity and scales. Thanks for your listening. Please refer to our paper and codes for more details.